you for coming. I will continue my lectures on mostly I will talk about the category of representations of a poset or of a quiver. I feel very much like I'm on stage. I'm connected wireless to the audio. The iPad is connected wireless to the screen. So this is not how we usually do lectures in mathematics. We have the general framework was that we start with a finite data set. We compute this filtered system of topological spaces by increasing slowly the radius of the balls around each point. So we get a filtered system indexed over the non-negative real numbers. And we associate the homology group to this. And the homology group really then is a vector space for every real number epsilon, and for any pair epsilon smaller to epsilon prime, we really do get a linear map between those vector spaces. So altogether we get what is called a module over R as a poset. Yeah, and then we said like first, when we have a finite data set, there will be only finitely many steps epsilon where the data changes essentially. So we can focus on these finitely many steps between. There's a continuous variety where everything is isomorphic. We can ignore that. So really that homology will give me really a module, a representation of this quiver, 1, 2, 3, up to n, a finite quiver. So we can focus on that. And this is the framework of one-parameter persistent theory, which I still want to discuss today. And eventually, I like to move on to bifiltrations to two-parameter persistent theory. So that's more or less what we had. And then we said, like, for one-parameter persistent theory, this module of this quiver AN will decompose into a sum of indecomposables, and the indecomposables are given by such intervals. And these intervals I can visualize as intervals, some information that they call the barcode of the module. And that's the general framework of persistent theory. So I was going to go into the details. What does that actually mean? I mean, what does it mean? M is isomorphic to the direct sum of a couple of other modules. So I really go into the details of this category of representations of a poset or category of representations of a quiver. So that was basically, this is what we want to understand. So I go back to the basics, to the fundamentals of those constructions. We had discussed already yesterday the notion of a direct sum. So the first thing, M is isomorphic to a direct sum of indecomposables. So first, what is a direct sum? So in the direct sum of two representations, I call them representation or module. These two are equivalent for me. Yeah. Either I say sometimes persistence module, sometimes it's a representation. So the direct sum is given by direct sums at each vector space, and the maps are just put on the diagonal. This is what we did yesterday. Yeah. And then next thing after that will be to define the notion of a morphism. Okay. So this is kind of my main point today when we want to consider category of representations. It's very important, very essential, not only look at the objects which we define, the representations, but also look at some permissible maps between them. They are called morphisms. So the objects, together with their morphisms, they form the category. And it's very important. A lot of information, essential information, sits in the morphism part. So that's my main point today. So let's start with the definition. Given two representations, M and N, over the poset P or equivalently over a quiver Q. A morphism between these two representations F from M to N is given by the following data. First, we have at every vector space, at every point, we have a vector space for M and a vector space for N. So a morphism is first given by linear maps between these two vector spaces. A morphism F is given by a family of linear maps F indexed X from Mx to Nx. And then we don't have arbitrary such collections of maps, then we want to have some compatibility condition, namely, whenever we have such a structure map between mx and my, so the module gives me a linear map here, mxy, and the module n gives me another such map, and I do have these morphism maps fx and fy. So whenever I have a pair x smaller equal y, or whenever I have an arrow in the quiver, I get such a configuration. And the condition is that this diagram commutes. Yeah, so going this way around or going that way around amounts to the same result. So I have a bunch of commutative diagrams that constitutes the notion of a morphism. Okay? So if I go back to the example that we considered yesterday, yesterday we were constructing the direct sum of two modules. There was a module M, sorry about this. There was a module M, which looks like this, and there was a module N that looks like that, and we constructed the direct sum. Now I want to look at them separately, and just decide, are there morphisms from M to N, or are there morphisms from the other way around, from N to M backwards, yeah? So here are two such examples. A map from M to N is given by maps component-wise, so from K to 0, from K to K, and from 0 to K. At every component, I get a map of the vector spaces, yeah? And the map from K to 0 is the 0 map. I have no choice. The map from K to K, well, I can choose any parameter. I choose the parameter 1, okay? And the map from 0 is the 0 map. This is the only choice. And G goes the other way around. So I have the 0 map here. I have the identity. I have the 0 map here. Okay, good. So I gave you ample of time to look at these two examples. Can you see the examples? Yeah, this is well visible. That's very good. So I have two such collections of maps, and now I ask you the questions: are they morphisms? So do they satisfy that commutativity relation at every single square that you can see? So let's do this democratically. So I ask you the question, first F, then G, is it a morphism? And you raise your hand, and then we decide by some crowdsourcing which one is a morphism and which one is not. That's good? Okay, good. So first question, F, is F a morphism? Please raise your hand. You're not very convinced. So we decided by democracy that F is not, I want to write, we decided that this one is not a morphism. Okay. It's not a morphism because if I look at it, if I start, say, here, then I go this way around, I factor through 0, so that composition will be 0. And if I go the other way around, I compose 1 with 1, so that composition will be 1. Yeah, but 1 is not 0, so that does not commute. Yeah, we do not have commutativity here, neither there. That is not a morphism. Thank you very much. Okay. What about G? If you think G is a morphism, raise your hand. Yes? Okay, perfect. We decide that this is a morphism because the diagram commutes. If we go around this way, if we start in 0, we get 0. If we go around that way, 0 goes to 0. And here, everything ends in 0, everything ends in 0. This is a perfectly well morphism. So that already is very important, that this this notion of morphism is not symmetric, right? I mean, I have a morphism from n to m, but I do not have a non-zero morphism backwards. Yeah. So that's important. This is kind of non-commutative. Okay. That's very good. You will have to remember this notion of morphisms. We will need this all the time. Okay. Good. So morphisms, very fine. Where are we in our general program? We said in our general program, maybe we want to understand M is isomorphic to a direct sum of some indecomposables. So we defined the notion of a morphism. Now, what is an isomorphism? An isomorphism is a morphism where all the maps are invertible maps. Yeah, if all the maps are invertible maps, then there is an inverse morphism. I can go back and forth. Yeah, so a morphism in this category is called an isomorphism, and we do write M is isomorphic to N with these symbols if there is a morphism where all the maps are invertible maps. Yeah. So I promised that I will try to use as background only linear algebra for these lectures. Yeah. And so in terms of linear algebra, I have a vector space here, mx, and I have another vector space here, nx, and I do a base change, right? So I do a base change on that side, and I do another base change on the other side. And this is one of the worst parts if you teach linear algebra. So I have my matrix here. What's the matrix below here after the base changes at the two vector spaces? So that matrix is going to be the same as I start here. I use fx inverse. I take mxy and I apply fy. So I get this formula. The matrix down here after the base change is obtained in that way. You see the formula? Yeah, so this is linear algebra. I just apply base changes in all of the vector spaces, and I accordingly change my matrices. Yeah, that's good. We can do that. So let's do an example. I take my two representations, M and N, the ones which I had before, and I give myself another representation, which I call L. L is this one, yeah, given by three vector spaces and linear maps, 1, 1, and 1, 1. And then I want to test, is this L isomorphic to the direct sum? The direct sum we computed yesterday, the direct sum is given by this. This is the direct sum, so it's given by these vector spaces and these linear maps, these matrices. And I want to verify, is there an isomorphism F between L and the direct sum? Yeah. Is L isomorphic to the direct sum of these two modules? Okay. So to find an isomorphism, I apply a base change at every of the vector spaces. So my base change from k to k, I don't have much choice. Let's take a 1. In particular, if my field has two elements, I really have no choice at all. Okay, so it must be invertible. Yeah. So my base change here is identity. My base change here is identity. Very good. So I ask you, what can we put here? So the base change that we can put here in the middle should be a base change that transforms this matrix into that matrix. That's what we want. So it transforms this matrix into that matrix by our formula above, means I compose these two morphisms. So I multiply 1, 1 with the matrix that I want to put here, and I should get 1, 0. Okay? So I give you this matrix. I give you that matrix 1, 1, and you want to do some row operations. I mean, you multiply with some invertible matrix from the left. You do row operations to obtain a matrix 1, 0. So what is the row operation that you would apply? Yes? So thank you. Oh, I lost everything. Oh, yeah. So my matrix that I put in here, yeah, should be an invertible matrix. And we want to do, what is your matrix?
It's like 1, 0, 1 minus.
Yes. So we keep the first row, good. And in the second row, we take the sum of these two, which is 0. Fine. Okay. Over the field with two elements, it would be 1, 1, 1. Yeah. So let's do this. This is perfect. Thank you very much. So we put in the base change 1, 0, 1, negative 1, and then 1, 0, 1, negative 1 would give me the desired result. I did the base change for the left-hand diagram. Very good. So what makes things more complicated in representations of quivers? We don't have one matrix, but we have a bunch of matrices. I do apply one base change for some diagram. This has an effect on both sides. Yeah. So this is the thing that goes beyond what you do in linear algebra. In linear algebra, we consider one matrix, sort of the representations of a quiver with one arrow. But in general, we have many arrows. So the effect of the base change here is the desired effect, but we do have to verify it also does the good thing on the other diagram, right? And I set up the example so that it works. So if you do the same calculations here on the right-hand side, so we want to compute this one and that one. Is this what we want to compute? In Z2 it works. Let's say we work over Z2. Yeah. And I think this what I wrote down here is actually not correct. So what is it? What is it that I have to verify? I want to verify that the matrix 1, 1 is the same. So I go that way around. This gives me 1, 1. And I want to verify this is the same as this composition, right? So this composition would be 0, 1, 1, negative 1. Multiplied with 0, 1. And what do I get if you perform this operation? You do get 1, 1 on the left-hand side and 1, negative 1 on the right-hand side. Yeah? This is correct? Okay, perfect. Very good. Let's say we work over the field Z2. And then everything is correct. And you figure it out over the complex numbers what you need to put. Okay, that's good. So that worked. Good. So next thing, so we know morphisms, we know isomorphisms. The next thing we need to study is when do we call a representation indecomposable? We call it indecomposable if we cannot decompose it. Yeah. A representation is indecomposable if it's not isomorphic to a direct sum of two smaller representations of two non-zero representations. Yeah. That's the notion of an indecomposable representation. And we have the big theorem, which goes back more than 100 years, that in categories of finite dimensional modules, I mean, our representations are locally finite dimensional. They are finite dimensional vector spaces at every point. So in such a category of finite dimensional representations of quivers or of posets, theorem by Krull, Remarque, Schmidt for the case where P is finite, and there are other works for infinite posets as well. We have the following result. So whenever you give me a representation M, then there are indecomposables. There's a family of indecomposables, Mi, indexed over some index set X, such that the given module M is isomorphic to a direct sum of these indecomposables. And up to here, this is not a very surprising result. I mean, you give me a representation, either it is already indecomposable, fine, or if not, I can decompose it into two smaller parts, yeah? And then I take the two smaller parts, they are either indecomposable, yes, if not, I decompose them further, and by finiteness, eventually, this process has to stop. So every module decomposes. The important part is they are unique up to isomorphism, yeah? There's only one way to decompose your module into indecomposables. Up to isomorphism, you could replace an MI by some isomorphic one, because the whole notion of here is independent of isomorphisms. But the thing is really, up to isomorphism, my module is uniquely determined by which indecomposables it is made up of. I cannot, this is like a unique factorization theorem for natural numbers. Yeah, I mean, the decomposition into indecomposable summands is unique up to isomorphism. Up to isomorphism, like for natural numbers, I mean, you can 15, you can factorize as 3.5, but you could also factorize it as -3 times -5. So there's always some isomorphism involved, but the factors are unique up to isomorphism. That's the big theorem. Very good. An example is said to be found on the previous slide. Yes, on the previous slide, we saw that my module M is isomorphic to the direct sum of two other modules, of two smaller modules, M and N. And you can verify those M and N, they are indecomposable. In fact, they are very small. And how would you go to decompose? I mean, the vector space K, you cannot decompose any further. Yeah, there's not a half-dimensional vector space. So these are both indecomposables. So this is the unique factorization of L into a sum of indecomposables. There's no other way you could obtain L from summing up some different indecomposable modules. That's the main point of the theorem. Okay. The problem is that I was a little bit cheating here. I mean, I gave you L, and I knew already it would decompose into these two guys, and then I ask you just a question: find an isomorphism. Yeah, finding an isomorphism that can be done in an efficient way. I mean, the calculation which you did, you can give it to a computer. I mean, in general, you look for an isomorphism. This is given by invertible matrices. They are given by some coefficients, and the coefficients need to satisfy some linear equations. So this boils down to a problem of linear algebra. Given two modules, find a morphism, find an isomorphism. This is a question of linear algebra. Yeah. However, if I didn't know beforehand these are the two good candidates, then it's very complicated. I mean, the theorem tells me that there exists indecomposables. The theorem doesn't tell me where do I find them or how do I look, how do I look for them. Yeah. And in general, if you have given a representation, it has a large dimension. And in general, I could look for possible ways to decompose them. But in the first problem, I do not know the index set. Yeah, I do not know how they could possibly look. And even if I would know a good index set of possible candidates, if my module has a high dimension, there will be exponentially many ways to sum up that module from smaller dimension vectors. So that's never going to be an efficient algorithm. Yeah. So in general, it's just looking at random, how could I decompose it? This is not a good way to view it. And I would say, so if I ask myself the question, how do we find those summons in the first place? If I'm just given L and I do not know these two, how do I find the possible summons? Then the main message is that morphisms are important in the category. And I would, instead of looking at my module M, I would look at what is called the endomorphism ring. So the set of all morphisms from L to itself, the endomorphism ring, and I would really study the endomorphism ring of that modules, and the endomorphism ring from its structure will reveal how the module decomposes or if it is indecomposable. So that's really the message, and this can be done relatively efficiently, yeah? So the message is really, instead of looking at the module L itself, I would look at the set, the collection of all of its morphisms from L to itself, study this ring, and then I will understand if it's decomposable and how it decomposes, yeah? And I might want to give you such an example in the problem session. Are you ready to do some calculations? Yeah? Okay, so we can do that later. That's the main point. Instead of looking at the module, look at its endomorphism ring. You will understand the module much better. Okay? Good. Okay, fine. Now, however, there are some situations, I mean, that was the general theorem for a general poset P. And in the general situation, I only do know that decomposition exists and it is unique, but I don't know how these guys will look like. I really have no clue in general, okay? However, there's some situations are much better understood. And this situation for posets is the situation where the poset is totally ordered. So in our example, we had the positive real numbers, or you can take the finite poset ordered 1, 2, 3, 4 up to n. In these situations where the poset is totally ordered, and this is a theorem that is for the finite case well known, for the infinite case, this is an example in Gabriel's book, and it has been published in the TDA literature by Botnan and Kolibuvi. So the general result for a totally ordered poset is the following. We know the indecomposables in this case. Every indecomposable is a module of a very particular form called an interval module. The notation for this interval module is k subindex I, the interval. So for some interval I of the poset, what is an interval in a poset when the poset is totally ordered? An interval is a connected subset, this one here, yeah? Everyone sitting between a starting point and an end point, that subposet is an interval. You agree this is an interval, right? And so when I have given an interval as a subposet, then I consider the module which is given by that interval, and this module is something like an indicator function, like a characteristic function of that interval. So the module, which is given by vector spaces, should be the one-dimensional vector space whenever I have a point in the interval and 0 outside. Yeah. So it's really the indicator module of the interval. Yeah. I'm one-dimensional along the interval, 0 outside, and the maps, the morphisms are identities wherever this is possible. So between any copies of K, I take identity map. So like this, I can create for every interval in my poset, I can create a representation Ki. They are indecomposable. You cannot decompose this any further. And every indecomposable looks like this. Yeah. So that's a very good, that's a very strong result. And so our general theory tells us any module decomposes into a sum of indecomposables. When the poset is totally ordered, these indecomposables look like intervals. So every module decomposes into a direct sum of interval modules. Now I would encode this sum of this set of intervals that appear in the direct sum decomposition of the module and into a set, and this set is called the barcode of M. And we visualize it as some bars, some lengths of intervals. And this barcode uniquely determines the module because we have Krull-Schmidt theorem. This collection of bars, this collection of intervals uniquely determines the given module. So that is our way how we arrive at the barcode for a totally ordered poset, okay? And example, there was an example 2 slides earlier, I say. So let's go back 2 slides, 1, 2. And here we had our decomposition and we work over the quiver 1, 2, 3. So this is totally ordered. And we have 2 interval modules. The module M is an interval module, right? So I can easily write M is the interval module. It's given by which interval? 1, 2. So M is the interval module 1, 2. And N is the interval module 2, 3. And I kind of decompose my given module L into a direct sum of interval 1, 2, and 2, 3. So the barcode, we can write this, the barcode of L would be the set of the 2 intervals 1, 2, and 2, 3. Yeah, so the barcode of L is 1, 2, and 2, 3. If this is my barcode 1, 2, and 3. Sorry, this is a bit of a mess. So these 2 bars are, this is the barcode of L. So we can do that. We have done it. That's good? Okay, perfect. So that works very well. And you can do this now in general for our persistence diagram. We start with the data set. And this is from Frederick's introductory article. I copy this from the article that is given in the summer school as the prerequisite material. So we start here with some data set. And in the beginning, we have just for every point, we have one single bar, and then we develop slowly we increase the radius, so we get this persistence barcode, and I can really interpret the persistence barcode in the way that we compute homology. Homology is a representation over a quiver with finitely many steps. I decompose it as a representation of this quiver. I get indecomposables. The indecomposables are characterized by intervals, and I just write down those intervals here into one picture, and this is the barcode. Yeah? Question?
So these are the barcodes.
Yeah, the red ones here, red is H0, and the blue ones here is H1. Yeah, you kind of you kind of should only look at this picture. Yeah. I mean, this is only the homology group of the first time step. Here we have discrete data points. Yeah, they are discrete. There's no H1. This only shows you how the things develop over time. Forget that. This is the barcode. Okay, good. Yeah, good, perfect. So we are finally back to have a really concrete understanding of that thing. What does that mean? And here are my interval modules. Okay, good. We are here. Okay, so let's go a little bit further. So things work really nice when we have a totally ordered poset. When our quiver, say, is a totally ordered quiver like this. When we have a finite totally ordered quiver, then the quiver really looks like that. And in that case, we know all the indecomposable representations. They are given by intervals. And for any such quiver with endpoints, there is only finitely many intervals possible. So the set of intervals, which is the set of possible indecomposables, is a finite set. Yeah. So that means that quiver of type AN is what they call representation finite. There's only finitely many indecomposable representations. That's one example of a quiver that has only finitely many indecomposable representations possible, right? And let's go back in time. Gabriel, 1974, looked at any finite quiver and asked the question, but which of those quivers are representation finite and which are not? Yeah. So we have seen this example. Linear type AN is representation finite. Yeah, I have only the intervals. And in general, you can characterize a quiver as representation finite, means it only finitely many indecomposables, if and only if this is a quiver of Dünkin type, of one of the Dünkin types A, D, or E. Okay, so there are the Dünkin types A, which are given by just like a line, but with any orientation. This could be this way, that way. I don't specify the orientation along. So any quiver that is a line with any orientation is called a quiver of type AN. In all these cases, there are only finitely many indecomposables. In the Dn situation, Dn is not a line. There's a branching point right here in the beginning. So these Dn quivers are representation finite, and the quivers E6 and E7 and E8. So here is E6 and here is E7 and this one is E8. These are three quivers. They are representation finite. Yeah. And so these Dünkin types appear in many branches of mathematics. They are linked to study of quadratic forms. They appear in Lie theory. So there's a beautiful theory of Lie groups and Lie algebras, and there's a classification of simple Lie groups and of simple Lie algebras, and they are linked to some graphs. And these graphs are called Dünkin graphs, and the Dünkin graphs characterize the simple Lie algebras. Okay, and there are Dünkin graphs of type A, B, C, D. So there's a gap. There's some don't appear here, and so there's a link between those simple Lie algebras and the quivers here, namely the representation finite quivers are exactly those corresponding to the simple Lie algebras of these types. And the link is in fact more detailed because you can count the number of indecomposables for each of these quivers. And in Lie theory, I don't go into this, but in Lie theory, there's a system of roots for a Lie algebra, and they come in two sorts. There's positive and negative roots. They have equal cardinality. And if you just count the number of positive roots, then you do get the number of indecomposables for these quivers. So there's some integrate relation between Lie theory and these quiver representations. This really fits very well to each other. And it's not just a coincidence. It's not just that the numbers happen to be the same. There's even a more precise relationship. Every of this positive root you can write as a linear combination of simple roots. And this linear combination is exactly what you get here as the dimension vector of the indecomposable. So there's a very precise relationship between Lie theory and representations of quivers. Yeah? Mm-hmm.
So the second is the
Always, yeah?
but then interval would be consecutive sequence of simple roots.
Yes.
Then if you take 1, 2, and then you are n minus 1 to n,
Mm-hmm.
this would still be a sum of simple roots, but not necessarily decomposable.
Yeah. This is decomposable. So if you have an interval that only lives here and there, then you can decompose it into that plus this one. Yeah.
Say that if you suppose the other constant roots, then they need to.
The indecomposable representations correspond to the positive roots. Not every combination of simple roots is a positive root. Yeah, I mean, there are some conditions attached to it and some integrate conditions, and the conditions exactly match the description of the indecomposables. That's the magic, yeah. So I don't go into Lie theory, but it's not true that every combination of simple roots is a root, no. Yeah, there's a complicated geometric picture, and it's exactly that what you need. Yeah. Okay, good. So this is the general theory which we do not need to be concerned with too much here. We are here mainly interested in AN. Yeah. For the AN type quivers, we do know that all the indecomposables are given by intervals. Yeah. Not only when the orientation is like this is what we had before, the poset, but also when for any possible orientation that you can choose, the indecomposables are always given by specifying an interval. Yeah, I specify some interval. I give myself k everywhere here and 0 everywhere outside. This is an indecomposable module, and they are all given in this form. For the other types, D and E, there's finitely many indecomposables, but they are not all given by intervals. Yeah. So for instance, in type D4, D4 has 1, 2, 3, 4. This one is D4. In D4, I give you an example here. There is an indecomposable module, this one here, which is not given by an interval. It's not the indicator module of any subset, because see here, there's a two-dimensional vector space. Yeah, the indicator modules are just, I put one-dimensional vector spaces wherever I have the subposet. Yeah, that one here is certainly not of this form. So there are modules which are not interval modules, but are indecomposable. I leave it to you as an exercise. Compute, this is an indecomposable module. However, so what we see here that the barcode description is available exactly here. Yeah, not there, not there, and not for anyone else, because for all the others, we have infinitely many indecomposables anyways, and they are not given by intervals. Yeah. So we are kind of lucky that the barcode description, the beautiful barcode description which appears naturally in TDA and which is linked to the study of the totally ordered poset, this is exactly the case where of type AN, where every module is given by an interval. Yeah. For every other poset, we are in trouble. Yeah, for every other poset, there is no such a nice description. There's no barcode available. Yeah, so that's kind of what I was trying to say here. Hmm?
It doesn't matter the orientation, right?
It's independent of the orientation. So for the AN here, I can have any possible orientation. I can choose this one, this one, this one. Whatever is the orientation, every indecomposable is given by just specifying some connected subset here. Yeah, some interval, and you put K everywhere here. So really the AN quivers are precisely those where we have a nice barcode. And so this is when we have this one parameter persistence module, we have the nice barcode description. But when we go further to other two parameter persistence, or we study other filtrations by other posets, there is no barcode. And if there's no barcode, we have to do something else. So we kind of finished this part, yeah, when we have a filtration which is given by one parameter along a line, along AN. We do have a barcode. We compute the persistence module. We do have a barcode. Very nice, yeah. And if you are in any other situation, if you have a bifiltration, a more complicated filtration, then there is just no barcode. And then we have to develop some other machinery, some other tools. Yeah. And that would be the multiparameter persistence theory. And instead of the full decomposition, we have to look at, you give me a module, a persistence module, I want to say something intelligent about it. I cannot fully decompose it. I cannot give you a nice barcode description, but I still want to get some information out of it. And then I would resort to looking at some what they call invariants, at some, I want to attach a vector to the module, like we heard in the previous lecture. You want to understand the nature of the module by attaching some discrete, some vector, some numbers to it, and hopefully they describe well the topological features. Yeah, so that's going to be the goal when we do some multiparameter persistence theory later this week. Okay, I think we can stop here.